everyone. I am Dr. Manisha Verma, teaching physics in Acharya Narendra Dev College, University of Delhi. In my lecture series on thermal physics, in my last lecture, I had begun with a discussion on radiation. By radiation I mean black body radiation. In my last lecture, I had discussed what is meant by a black body, what is meant by a black body radiation, what is the spectrum of a black body, how can we interpret the spectrum in different regions. By different regions I mean low frequency region, high frequency region, low wavelength region, high wavelength region. I had also discussed what is the Kirchhoff's law, what is its proof, and I was on to discuss the applications of Kirchhoff's law. So, I will take it up from there, the applications of Kirchhoff's law. There are several examples which illustrates what Kirchhoff's law says. According to Kirchhoff's law, good absorbers are good emitters. That is, if the emissive power E of a body is greater, according to the Kirchhoff's law, the corresponding absorptive power also must be greater. This particular property can be seen at many places which serve as illustrative examples of Kirchhoff's law. Let me discuss the first such application. When a polished metal ball having a black spot on its surface is heated to a high temperature, the black spot shines more brightly than the polished surface. This is due to the fact that the black spot is a better absorber of radiation and hence accordingly it will be a better emitter. This is what Kirchhoff's law says, that good absorbers are good emitters. Second illustration. When a green glass plate is heated in a furnace, it appears red. Why does this happen? This happens because at ordinary temperatures, the green glass absorbs red strongly and emits green. At higher temperatures, it emits red. Similarly, if we take the reverse case, that is, if we take a piece of red glass, then we see that a piece of red glass glows with a green light when heated. Actually, red glass appears red because it reflects red light and absorbs rest colors from the white light. The effect of visible spectrum minus red is green. Hence, the red glass emits green on heating, which it has absorbed when it was cold. One success of Kirchhoff's law is by an explanation given to explain the characteristic spectrum of every element. So, the Kirchhoff's law established that the atoms of every element give a characteristic spectrum. Thus, the presence of the characteristic spectral lines in a spectrum indicates the presence of that element in the substance of which the spectrum is taken. To elaborate this further, let me concentrate on the spectrum of the Sun. In the Sun's spectrum, a number of dark lines in the solar spectrum called the Fraunhofer lines are seen. The presence of these lines can be explained on the basis of Kirchhoff's law. Now, what is the Sun? The Sun consists of a central glowing mass that emits continuous spectrum. However, when the radiation from the inner regions of Sun passes through relatively cooler solar atmosphere having different gases, the gases absorb radiation of their characteristic wavelength. Not every wavelength, only certain wavelengths. As a result, these wavelengths are absent in the solar spectrum. These regions appear as dark lines. During total solar eclipse, these lines appear very bright because the rest of the spectrum is dull now. If we know the wavelengths of these lines, the presence of different elements in the solar atmosphere can be easily found. So, this is one very important applications of Kirchhoff's law, where we see that Kirchhoff's law is verified, and it's a very important law, as I mentioned earlier, and it is the first law to understand what are the various important properties of black body radiation. Now let me move on to the second law, which can explain the black body spectrum to a certain extent. This law is very important and is called the Stephen's law. Now let me make it clear that we have the Stephen's law and the Stephen's-Boltzmann law. Basically, both these laws say the same thing. It is only that Stephen-Boltzmann law is an extension of Stephen's law. According to Stephen's law, the total energy emitted per second per unit area E of a perfect black body corresponding to all wavelengths is directly proportional to the fourth power of the absolute temperature T of the body. This means that if we have a black body maintained at a temperature T and we are able to measure the total energy emitted by this black body, of course, this energy emitted has to be taken per second per unit area, and if we represent this particular quantity by capital E, then E is proportional to T. This is a very important and significant result pertaining to black body spectrum. So, what do we have? We have E is proportional to T4. To remove the proportionality sign, we have to introduce the proportionality constant, and this constant is denoted by sigma. Sigma is a constant of proportionality and is called Stephen's constant. The value of sigma is 5.67 into 10 to the power minus 8 watts, meter minus 2, Kelvin minus 4. It is easy to remember the numerical value of sigma. Please see the figure again, 5.67 into 10 to the power minus 8. So, all you have to remember is 5, 6, 7, 8, and then you will never make a mistake while using the value of sigma in various problems. If Q be the total amount of heat energy emitted by a black body, then we have Q is equal to A into T into E, which gives us A into T into sigma T4. Why? Because E is equal to sigma into T4. Now, as I mentioned just now, Stephen-Boltzmann law is effectively an extension of Stephen's law. So, according to this law, the net amount of radiation emitted per second per unit area of a perfect black body at temperature T is equal to the difference in amounts of radiation emitted per second per area by the body and by the black body enclosure at T naught, that is E prime is equal to E minus E naught. So, effectively we are saying that we have two black bodies One is at a temperature T and the other is at a temperature T naught, such that the black body at temperature T is enclosed by the black body at temperature T naught. So both of them will emit radiations as given by Stephen's law. That is, E will be given by sigma T4 and E naught will be given by sigma T naught 4. Hence, E prime will be given by the difference of both E and E naught. So we have E prime is equal to sigma T4 minus sigma T naught 4, which gives me sigma T4 minus T naught 4. Proceeding as above, we can say that the total energy lost Q prime will be equal to E prime A into T is equal to AT. E prime is what? Sigma T4 minus T naught 4. So we substitute the value and we get that Q prime is equal to EA T sigma T4 minus T naught 4. That is, we can say that the total radiation energy emitted per unit surface area per unit time from a black body is proportional to the fourth power of the absolute temperature of the black body. If I use the word net radiation, I can use the word net radiation also instead of total radiation. When I talk of total radiation, I mean the Stephen's law, and when I talk of net radiation, I mean the Stephen-Boltzmann law. Because in Stephen's law, we consider only one body, whereas in Stephen-Boltzmann law, we consider two bodies. Now, let me give you and explain the proof of Stephen-Boltzmann law, a very interesting proof. The proof of Stephen-Boltzmann law is based on thermodynamical considerations. Let us consider an enclosure of volume V containing black body radiation at a constant absolute temperature T. Now, the black body radiation has some energy density. Let this energy density be U and let P be the radiation pressure. In my last lecture, I had discussed what is small u, what is the radiation pressure in detail. Hence, if we denote the total energy of radiation in the enclosure by capital U, then we have capital U is equal to small u into V. Also, if the radiation is normal in nature, then we take the pressure is equal to energy density U, and if the radiation is diffuse in nature, we take the radiation pressure P as U by 3. In this case, we take the radiation as diffuse, so we take P is equal to U by 3. What does the first law say? According to the first law of thermodynamics, we have dq is equal to du plus p dv. So what is capital U? Capital U is small u into V. What is pressure P? P is U by 3. So let me expand the differentiation and I get U dV plus V du plus U by 3 dV. So we have two terms which have dV in them. Combining these two terms, we get dq is equal to V du plus 4U by 3 dV. From the second law of thermodynamics, we have dq is equal to TdS. This means that ds is equal to dq by T. dq we have just found out is V du plus 4u by 3 dV. So, substituting the value of dq in this, we get ds is equal to V by T into du plus 4 by 3 into u by T dV. To solve further, let us take entropy S as a function of u and V. We can then write S is equal to S function of small u and V. If we expand this, we get ds is equal to delta S by delta u at constant V into du plus delta S by delta V at constant u into dV. If we compare the equations, we get delta S by delta u at constant V is equal to V by T and delta S by delta V at constant u is equal to 4u by 3T. So, we have two equations. First equation is the derivative with respect to u at constant volume, and the second derivative is with respect to volume at constant energy density. Since ds is a perfect differential, we have that if we take the double differential, it will not make any difference to the value. So, we now have delta square S by delta u into delta V is equal to delta square S by delta V into delta u. What is meant by this? That the order of differentiation does not matter. To illustrate this point, to apply this feature, we differentiate equation 1 with respect to V and we differentiate equation 2 with respect to u. We then get delta by delta u into 4 by 3 u by T is equal to delta by delta V into V by T. On differentiating, we get 1 by 3T is equal to 4 by 3 u by T square delta T by delta u. So, what do we get? We get delta u by u is equal to 4 times delta T by T. If we integrate this, we get log u is equal to 4 log T plus log A. Log A is the integration constant. So, effectively after integration, we are getting u is equal to AT4, A into temperature raised to the power 4, which means that the total rate of emission of radiant energy per unit area is proportional to the energy density. So, we have E is equal to UC by 4. But what is U? U is AT4. So, effectively if we substitute the value of U, we get E is equal to AC by 4 into T raised to the power 4. We denote AC by 4 as a constant sigma. Why do we denote? Because if you see carefully, A is a constant, C is the velocity of light, which again is a universal constant, 4 is a constant. So, if we have 3 constants, we can denote it by a single constant, and this constant in this case is nothing but the Stefan's constant. So, we have E is equal to sigma T4. Sigma is AC by 4 and the value of sigma is 5.67 into 10 to the power minus 8 joules, meter minus 2, second minus 1, Kelvin minus 1. We can denote it in terms of watt also. It is not difficult to remember the value of sigma. You just have to remember 5, 6, 7, 8. Now let me do a very interesting question, very interesting application of a property of black body radiation which follows from the Stefan's law. What is the problem? The problem is, show that during the adiabatic expansion of a black body, Vt cube is equal to a constant, or we can say V 1 by 3 into T is a constant. So, let me prove this. The first law says that delta Q is equal to du plus PdV. We are talking of an adiabatic process. So, delta Q has to be equal to 0. So, we now have du plus PdV is equal to 0. What is capital U? Capital U is small u into V. Repeating again, capital U is the total energy of the black body. U is the small u is the energy density of radiation. Capital V is the volume of enclosure. So, if we expand duV on the left hand side, we get two terms on expanding the differential, and if we combine the two terms which have dV in them, we get 4 by 3 u dV is equal to minus V du. If we integrate this equation, we get 4 by 3 log V is equal to minus log u plus C. So, we get u is equal to 84. This means that log of V 4 by 3 into u is a constant. But what is u? We have just seen that u is equal to AT4. So, we get log of V 4 by 3 into T4 is a constant. The constant in u is equal to 84, A is taken care of on the right hand side. So, just simplifying further, we get V 1 by 3 into T is a constant. This means that if we have an enclosure maintained at temperature T and it is emitting black body radiation under adiabatic conditions, and if V be the volume of that enclosure, we have V raised to the power 1 by 3 into T is a constant. I hope this is clear. I hope you have understood what is the Stefan's law, what is Stefan-Boltzmann law. I will discuss more laws in my subsequent lectures. Thank you.